Here's Rakia, and in this tutorial I'll be showing how Tensorflow Js became a performance bottleneck for my web application. I've put a link in the description of the video to an article with more details if you want to check that out. So, to get started, let's come back to the beginning of the story. In the last couple of months, I have implemented an application and used it to show how to navigate between the order creation steps with hand gestures instead of mouse click, as you can see here. I'm giving now instructions to the app to go to the next or previous step with my hand. But although I've used Angular best practices in the implementation and I have unsubscribed from all my event listeners, I have recently noticed that my app became sluggish and the user experience was very slow and terrible. So, as a starting point to investigate the memory usage, I checked the performance timeline record on Chrome DevTools. And this is the result. The line representing the number of frames per second, FPS, is almost totally red. The CPU consumption is about 100%, it's the yellow rectangle. The amount of scripting is very high, and the browser was busy for 47 seconds only with the scripting task. And the total blocking time, TBT, is over 18 seconds. It's in the bottom of the screen. I've witnessed it, in fact, in my career, some web application with poor web performance, but I've never seen such a terrible performance timeline. To visualize how the memory is distributed among the app's JavaScript, I've generated two heap snapshots. The first one just after starting the app and the second one after performing a short scenario. As you can see, unlike the first heap snapshot, which was less than 10 megabytes, the size of the second one was 110 megabytes. It has an increase of over 100 megabytes. As you may have noticed in the chart, there is over 90 megabytes of typed arrays. If you are curious to know what they are and where they are coming from, here is the answer. JavaScript typed arrays allow us to read and write raw binary data in memory buffers. They are array-like objects and could be int8 arrays, int32 array, they could be float32 array, they could be array buffer, data view, among other types. They are also used by WebSockets, web workers, XML HTTP requests, fetch API, file APIs. They are used by Web Audio API, WebGL, Canvas, and Media Source API. So let's come back to our second heap snapshot now and continue our analysis. Right here, I've discovered that tensor is one of the elements that are holding a big shallow size and a bigger retained size. Shallow size is the size of memory that is held by the object itself, and retained size is the size of memory that is released once the object itself, along with its depending objects, is deleted. So, tensor here reminds me of the Tensorflow JS library that I have added to my application to implement the hand gestures feature. And in case you don't know what Tensorflow JS is, it's an open source framework created by Google for training and using machine learning models in the browser. It helps JavaScript developers to build and deploy ML models within the client-side applications without ever setting up a server or even a database. The library is also a companion to its namesake TensorFlow, which is an ML library used with Python. This means that you can convert any TensorFlow machine learning model to run in the browser using TensorFlow JS. But I continued my investigation and found more insights in the heap profiler. I've seen that array buffer, which is typed arrays, has shallow size of 50 kilobyte and retained size of 90 megabyte, and it represents 82% of the total retained memory size. Int32 array has shallow size of 4 kilobyte and retained size of 9 kilobyte. Float32 array, they are also typed arrays, has shallow size of 51 kilobyte and retained size of 27 megabyte. It represents 24% of the total retained memory size. Encode matrix-based program has shallow size of less than 1 kilobyte and retained size of 77 kilobyte. With more search, it turned out that encode matrix-based program is coming from WebGL and Tensorflow JS, and that float32 array and int32 array objects are also used by WebGL, as you can see here. With this outcome, I went back to my app and removed the line of codes where I have used the TensorFlow library. Can you guess the result? The performance was drastically improved, and there was almost no increase in the heap snapshot after performing the same scenario that led to an increase of over 100 megabyte when the library was present. Do you want to know why? Here is the answer. Unlike TensorFlow, which only supports NVIDIA GPUs, TensorFlow JS works with any graphic card by using the WebGL browser API. This is an advantage of TensorFlow JS over TensorFlow, but as a result you lose a bit of performance, because WebGL can only be made to perform the matrix multiplications desired by TensorFlow JS with a few tricks. WebGL has no DOM, it has no CSS, and no layout impact. To see anything on the screen, the API requires a lot of script code. WebGL uses shaders, which result in additional requests and client-side load or compile time. WebGL pulls content down the pipe. And the consequence is that WebGL apps can be CPU suckers because of a lot of computation. So compared with TensorFlow, when using TensorFlow JS, we have to make trade-offs in terms of performance. And when this becomes critical, it's recommended to switch to Python, which is good news for Python developers. So now we'll finish this video by a little comparison, and if you have any question, just leave a comment below, and as always, thanks for watching.